It is recording now. Go ahead.
Okay. Hello everyone, as you can see now, this time we came to this very nice and cozy coffee shop to record this video for you. And by the way, I like their coffee, it's really great.
What are you talking about? It is certainly obvious that we're using green screen to remove the background.
Coffee shop?
Just remove what you said when you're editing the video. I'll repeat again.
Hello everyone, as you can see now, this time we came to this very nice and cozy coffee shop to record.
Why did you remove the background? To stop you and what you're saying.
But not everyone can see what is happening behind the scene.
Okay, I'll change it, but no coffee shop. By the way, talking about behind the scene, sometimes in machine learning you're dealing with sensitive and private information. And similar to what you're doing right now with green screen, you also want to make sure that no one will reveal those sensitive and private information to have this as a protection layer. Even for the train model through reverse engineering, you want to make sure your private information is safe there. Do you know how you can have this protection layer in machine learning?
Differential privacy. And yes, I would love to know how to do it in action.
Perfect, then let's check it out.
Hello everyone, this is MG and welcome to another video which we're going to showcase you how you can use differential privacy to protect your private information through using a deep learning use case in healthcare scenario. Let's check it out. So firstly, what is differential privacy? And when we talk about differential privacy in machine learning, what are the components we are considering here? In this chart that talks about the smart noise system, which is actually a solution for applying differential privacy on data, is that let's say me as a data scientist, as a user, I'll submit a query to a database and I want to grab some data for using in my training data set. And that data in a SQL database has some private data set. So how we can apply this differential privacy here is, first, I submit a query here and it will check if I have the credentials to access that database. Let's say my user and pass. And as soon as I pass those credential requirements, it will check the budget. So what does that mean, budget here? Because there's a risk that if someone can do infinite amount of queries to a database, even with limited access through those sub data set that I'm grabbing from all different various queries, there is a chance that I can reconstruct that database again from my too many queries and be able to reconstruct those private data. So that's a privacy concerns. That's why we can limit those queries with specifying a budget on the top of that. So when we query the data, we check if we are going over that budget limitation that we have specified or not, to actually limit the amount of queries, and also on the top, limit the risk of reconstructing the database and reconstructing those private data set from too many queries. So that's one thing. Second, as soon as the private data is actually called from a query, it will, through a mechanism, it will start to add noise. And then I will have a report from a data set that has passed the credentials, passed the budget, and also has some noise added. And now you might question that, well, if I add noise to my data set, I'm really missing the real value of the data. I'm just witnessing noise. Actually, that's a trade-off. If you add more noises, then your solution is more secure. The risk of revealing your private data is less because you have added more noise. But at the same time, you're losing a little bit of accuracy and validation of the data that you're querying from that database. Because of too many noise you have added, you are a bit far from the real value. So that's a trade-off, and that's a choice, that how much noise you will add to make sure first your data privacy is protected, and on the top, you're not too far from the real value. So now when it comes to machine learning, is it the only way that you can apply differential privacy, just some adding noise to the data and then train the model on a data set that has some noises? Or there are some different ways also we can consider as well. So here, this is actually a picture from a white paper called the Smart Noise White Paper, published by Microsoft, that show different stages of applying differential privacy in machine learning. Well, obviously the first phase during the data collection. when I'm collecting the data, we just saw the previous picture that was talking about the time that when I do the query, we can add some data there, some noises to that data. Or in the second stage, add the noise by itself to the data set that we're storing in the database. Or, which is the interesting part, is adding the noise during the training process. I mean the machine learning training process. This is the one actually we're going to see a hands-on example of this for deep learning. Or the time that you're dealing with multiple models, each of them through different training stages. When you aggregate those models, you can actually add some noise to protect the information there. So the example that we're going to use, let's say we're going to train a deep learning model that can predict a classification model that can predict whether given X-ray chest image is pneumonia or just a normal chest image. And we're going to train a model without applying differential privacy, and then training similar model, but this time with applying differential privacy. And then we can see first how we can apply differential privacy for this scenario, and on the top, how the results going to change when the time that we have differential privacy in our scope when we're training this deep learning model. So here is my notebook. Actually, I have opened my Azure Machine Learning Studio, and then I have created a Python notebook inside. For some of you, still Azure Machine Learning might be a new service or new tool that you have never used. If that's the first time you're seeing this, you can check out the part 1 of Azure MLOps video series in the YouTube channel. So it contains an introduction about this service. So I'm not going through explain the details, but again, using Azure Machine Learning here for this use case is not a must. You can use any IDE you want, or you can use your local machine. But now here, because I wanted to have GPU, so with the scalability of this service, I was able to, with a click, create a GPU machine that you can see the information about the number of the GPUs, the disk and RAM, so on and so forth. And now I was able to actually execute codes to also save the time. I ran the code, and now I'm going through the results and show you what I have done here with applying these codes. Also, I will add the link of the GitHub that I have grabbed these codes. So you can check that out if you want to execute by yourself and dig in a bit more. So the first thing that I did was installing this open source library that actually I'm using with PyTorch to apply differential privacy. So what is this library? This is basically a solution that I can wrap my PyTorch training to include differential privacy. And it has multiple components and parameters that I need to add to my training object to make it secure with differential privacy. I'll come to this later when we hit the part that I'm adding this in the code, but just telling you that why I need and what is this library that I'm installing here. Let me scroll a bit down. So I'm importing the packages needed for my training process. Also, I am importing the privacy engine from the library that I just installed. And for training, predicting some of those well-known functionalities of machine learning, I have added them from the GitHub code that contains those functions here. So when I say import this file, I have those functions like training here. When I call this, I'm able to train my model here, just showing you the code. So going back to my main notebook, I have already ran this code. I have imported all the packages, and here I told you about the chest X-ray images that I want to use for doing that classification or training the classification. So this dataset actually is coming from a well-known Kaggle dataset that I'm going to show you here. So I downloaded the file. I think that the size wasn't that huge, so almost 1.24 gigabyte, containing testing, training, and validation dataset. So I downloaded them all, and I have it also in the path that I have described here. So data. You can see there is a zip file here that I downloaded, and then I'm saying that this is the place I want to unzip the data set. So the unzip data set is inside the ML folder. I was able to unzip when I actually ran this code, and you can see, for example, for the test data set or train data set, I have the images for this both classes. Let's actually click on one of them maybe to see how it will show. So let's say clicking on the first one. The number of the images is a bit high, so that's why it is taking a little bit longer. And as you can see, for example, that's an image of a normal chest, the X-ray image. So let's close this and also close these tabs here to make it less busy. All right, I'm doing also some normalization of the size stuff, so that's why I have the mean and STD standard deviation, and then also I want to have the same channels and size of the height and width for the images. So that's why I'm having these variables here. And then with extract equal to true, it will start to unzip the data, which what will happen, and you saw that how the data set were unzipped, and now I have them ready to be used for training my model. So here, I'm using those variables that I defined on the top to do some transformation that I talked about, normalizing the data. And then after doing those normalizations, defining actually those normalizations, what I'm doing is defining my data loader, which is I want to have my training data set, validation, and test data set to be loaded from the path that I have specified here. I put the batch size for validation a bit low because of saving the time with validation process, but based on the amount of the data, the capability of the compute, you can certainly have different variables and parameters here. So after applying all those normalization, defining a data loader object in PyTorch, I am also executing this code that is basically clipping and then normalizing and then showing me just an example of how those data sets or images of both classes have been transformed. And now it is ready to be used for the part that I'm going to train the model. This is actually the architecture of the model. I'm not going through explain the details of CNN model, but that's a typical way to define different layers of convolutional network layers that we use for CNN. And with nibbled images, with max pooling, and also drop out for the normalization piece and making sure it will help us to have a less biased model. And then after defining the architecture of the model based on this information that you see here, this is the time that I can hit the train piece, but I'm not applying here any differential privacy here. Just through 15 epochs with the learning rate that I have defined with the Atom optimizer, I'm going to train the model and validate based on the validation loader to see how would be the model after training. So again, because of the very small batch size, you see sometimes there's a jump in the validation accuracy or validation loss, but just regardless of the results, we're going to see how it's going to be different when we apply differential privacy. For example, here we see that within the training process, when we were hitting more epochs moving forward, the training and validation loss were getting less and less. Again, because of those configurations just added to test, there are some jumps that is happening here, but let's ignore those and just see the flow, and then we can compare how it's going to be different when we apply differential privacy. So I've saved the model just in case, and I can load the model back, and then I have applied my metrics. I calculated the metrics to see how the model is performing. There are more digits after this, but in general, we can say the accuracy score was almost 94% when we didn't have differential privacy. Now, the time when we apply differential privacy, this is the moment we're going to use the library that we actually installed and utilize the privacy engine component that will help us to define how we're going to apply differential privacy here. You can see there are a couple of components here. First, well, definitely the model, the batch size, the sample size, so on and so forth. But you can see some components about differential privacy. For example, noise multiplier. What does that mean? Although it has been explained here, for example, here's the ratio of the standard deviation of the Gaussian noise we add. It is all about, in a nutshell, how much noise we will add for this scenario that we call it noise multiplier. But the question is where we add the noise. Well, there are two levels that I want to explain here, how we are applying this differential privacy within the training. You know that when we go through training, we have the weights, which are the parameters of the layers of my neural network that through back propagation, I calculate the gradient descent and I see how is my loss function is changing, or how much my model is predicting what it is supposed to predict and more close to the real value. So based on that, excuse me. So based on that, I can adjust those weights to come up with the model that whatever it predicts, it is closer to the real value. So when I validate the model. So when I calculate the gradient, let me actually explain this through a chart through a picture that is much easier to understand. So from the same Smart Noise white paper, here you can see that I have weight 1, and weight 2, which are we will have a lot of weights based on the size and dimension of my neural network model, but here let's say just considering 2 that we can plot it even better. Based on the weight that we have defined for the model that we're training, which we start with a random guess and then iteratively we'll make it better in a way that we will have less error. And error is a difference between true value and what the model has predicted. So we have to define those weights in a way that, let's say there's a hiker here hiking around and he or she is looking for the shortest way to come down to the valley. So what would be those weight choices that he or she, the hiker, can come all the way quickly to the valley in a faster way. So how we can do this? We can do this based on calculating the error or the cost function, which is the differences between true value and predicted value, and through calculating the derivative of those the loss function based on these weights, I can define what would be the next weight choice that we can help this hiker to come to the valley. This is called actually gradient descent, which gradient here is the derivative of the loss function with respect to the parameters here, which can be also weights. So we'll do this iteratively all the time, updating these weights to come up with a combination of the weights that reach to the point that the hiker is now in the valley. So getting back to the notebook, now we know that what is gradient and how we calculate this. But after the calculation, you will see that we will clip that gradient. For example, that extra amount has passed the threshold, so we have clipped this here. And then after clipping, I will also add another noise that we talked about to that calculated gradient descent to move that gradient a little bit in a different direction. So you might question why we are doing this. You know that when we are training a machine learning model, there is a chance that the model will not train actually the data set or learn the data set. It will actually memorize the data set. So if I train my model with the training data set too much, or if the architecture of the model is in a way that it can easily memorize my training data set, then that's a risk for me, because now I have a private data set that the model has memorized that private data set. So when I deploy the model somewhere, although I'm not directly providing my private data set, but the deployed model that you're exposing has memorized that private data set, so there's a chance that might be revealed. That's why I will stop my model to memorize and fully memorize that private data set. So instead, I want to make it more generalized and do not specifically get fully affected by a private data set. That's why I'm a little bit manipulating that gradient, calculated gradient, and also that can also affect the decision that I'm gonna have for the weights with clipping that and also adding a bit of noise. That's why I have a noise multiplier parameter, which is basically the amount of noise I can add. If you add more noises, more private solution you will have, but a bit less accurate model. And also the max level that I can define for my gradient. So if my gradient is more than that max, it will clip it. So when I define those and I attach it to my optimizer, the same thing. I'm training my model using PyTorch, the same optimizer, all the same, even the architecture of the model. And you can see the same thing I'm plotting. Within each epoch I'm going forward, well, the loss are getting decreased, but also there's an epsilon value that is increased. What is that epsilon value? Epsilon is a way that I can quantify a little bit, at least, how much my machine learning model is actually secure in aspect of differential privacy. So if I have more epsilon, it means that I have less private model, or I have applied less differential privacy component. So and vice versa. So that's why when I train more and more and more through the more epochs of to train my model with the same data set, the chance of having differential privacy in my solution is getting less and less and less. There's actually a nice picture that I can show and explain this epsilon value even better. So here in this, again, the same Smart Nodes white paper, let's say these are private information that we have from people standing here. And here on downside, we have this epsilon parameter. If I have a very, very low epsilon parameter close to 0, it means I have much more secure in that modeling aspect of differential privacy. But because I have added a lot of noises, the picture is blur. There are too much noises. A stronger privacy, but more noises. Vice versa, when I have a huge epsilon, I have less noise, but also less private, less stronger privacy. But less noise, I can see the picture more clearly. So that's the concept of epsilon that has been also applied to the wrapper that we use for differential privacy in PyTorch. And scrolling down all the way, now you can see my accuracy is less. I think it was 93, 94%, but now the average accuracy score is 75%. And even if I quickly calculate and plot the ROC curve, you can see that when I have no differential privacy, the situation is a little bit better. Again, because of the quick number of batch sizes and configurations I added, you will see the ideal scenario, but usually that wouldn't be the case. But just it is clearly showing me that because of the noise that I added, the performance of the model is a little bit degraded, but I have now a solution that has applied differential privacy on it, and I have more private solution with less risk that I can deploy and provide service. So basically that was just an example of applying this solution in applying differential privacy now for a deep learning scenario within the training stage. But again, as I mentioned, that's not the only way. Even for the initial training, when you want to query the data from a database, on the top of your query, we can add noises to the data. And then we can leverage the data set, not just for machine learning, for any data analysis scenario that you can do. Let's say you want to calculate some statistical information from the data. With the noise you add, yes, there would be a little bit changes on your statistical information or descriptive analysis that you do on the data. But again, you're still achieving something as well, which is differential privacy. And you can adjust this trade-off, that having a differential privacy versus an accurate solution with the amount of noise and differential privacy parameters that you can apply to the solution.
Alright, as you watched, this was just an example of applying differential privacy for deep learning in healthcare, but you can certainly do the same for a variety of different ML models and even data analytics use cases.
Quick question, MG.
Yeah?
Can you remove the background again now?
Okay.
So I know that we are cloning each other because of using green screen, and that's why we are two MGs here. But now you remove the background and no green screen anymore. Why we are still two MGs here? That doesn't make sense.
I cannot answer this.
Why?
Differential privacy. Kidding. I'll explain to you after recording the video. Until next video, take care everyone.